Hello friends, welcome to my second lecture on discrete Fourier transforms. We will first show that the vectors uk given by e to the power 2 pi I kn by n, where n varies from 0 up to n minus 1, it takes value 0, 1, 2, 3 and so on n minus 1, they are orthogonal, that is they form an orthogonal basis over the set of n dimensional complex vectors. So, in order to prove that the vectors uk form an orthogonal basis, we have to show that the inner product of uk with another vector say uk dash from the same set is equal to 0. Now, let us take two vectors uk and uk dash from this set e to the power 2 pi I kn by n, where n takes value 0, 1, 2, 3 and so on up to n minus 1. So, then uk is e raised to the power 2 pi I kn by n, uk dash is equal to e raised to the power 2 pi I k dash n by n. This n denotes the transpose, that means we are writing these vectors n vectors in the form of a column. Okay. So, that is why we have written that as e to the power 2 pi I kn by n. Okay. They are n vectors, we are writing them in the form of a column. So, now inner product of uk with uk dash, uk and uk dash belong to the n dimensional complex vector space, that is Cn. Okay. So, they belong to Cn. Okay. uk and uk dash belong to Cn. Okay. So, in Cn the inner product of uk with uk dash is defined as uk conjugate transpose into uk dash. uk conjugate will be equal to e raised to the power, iota will be replaced by minus iota. So, minus 2 iota k n by n. Okay. So, this will be uk conjugate transpose. uk conjugate transpose means we take the transpose of the vector. So, when we take the transpose of the vector, okay, then uk conjugate transpose will be row vector. Okay. uk conjugate transpose will be row vector and that will be given by e raised to the power 2 pi I k n by n, okay, where n takes values from 0, 1, 2, 3 and so on up to n minus 1. So, we can write like this, let us take n equal to 0 first. So, we can write 2 pi I k 0 by n, then e raised to the power 2 pi I minus we have to take because of this minus. Okay. So, minus 2 pi I k 1 by n, second component, and the last component is e to the power minus 2 pi I k n minus 1 over n. Okay. So, this is row vector uk conjugate transpose. uk conjugate is the column vector actually, this column vector where we have n components. So, let me write that as follows, we write it as in the form of a column vector. So, we have its components as e raised to the power 2 pi I minus 2 pi I k 0 by n, e raised to the power minus 2 pi I k 1 by n, okay, e raised to the power minus 2 pi I k n minus 1 by n, n minus 1 divided by n. So, this is the column vector uk conjugate. When you take transpose of this conjugate vector, actually these uk's are all n belonging to Cn. Okay, they are all belonging to Cn. K varies from n varies from 0 to n minus 1. They all are vectors in Cn. Okay. So, uk conjugate transpose is this. When you multiply by uk dash is what? uk dash is column vector. Okay. So, e raised to the power 2 pi I k dash 0 divided by n, e raised to the power 2 pi I k dash 1 by n, and so on, e to the power 2 pi I k dash n minus 1 divided by n. Okay. So, when you multiply uk conjugate transpose with uk dash, okay, this being 1 by n matrix and this being n by 1 matrix, when you multiply you get 1 by 1 matrix, that is you get this summation sigma n equal to 0 to n minus 1 e to the power 2 pi I n. Okay. This 0, n varies from 0 to n minus 1. So, that we write as n. So, e to the power 2 pi I n and that k dash minus k divided by n. Okay. So, 1 by n into n by 1 matrix gives you n 1 by 1 matrix, and here when you sum this series, this is a geometric series. Here you can see that if k is equal to k dash, okay, if k is equal to k dash, e to the power 0, okay, will be equal to 1, and this is n is varying from 0 to n minus 1. So, this total sum will be then n. Okay. So, if k is equal to k dash, this is equal to let us do it here, we have sigma n equal to 0 to n minus 1 e to the power 2 pi I k dash minus k into n divided by n. Okay. So, this is actually a geometric series if k is not equal to k dash. If k is, let us first find the sum when k is not equal to k dash. So, this is equal to 1 minus e to the power 2 pi I k dash minus k raised to the power divided by n raised to the power n. Okay. The geometric ratio here is e to the power 2 pi I k dash minus k divided by n. Okay. And so, this divided by raised to the power n divided by 1 minus e to the power 2 pi I k dash minus k divided by n if k is not equal to k dash. Okay. And this will be equal to 1 minus e to the power 2 pi I k dash minus k, alright, divided by 1 minus e to the power 2 pi I k dash minus k divided by n. Now, k and k dash are integers. So, e to the power 2 pi I k dash minus k will be equal to 1. So, we have 1 minus 1 divided by 1 minus e to the power 2 pi I k dash minus k divided by n. Okay. Because k and k dash vary from 0 up to n minus 1. Okay. Now, so this is equal to 0. So, when k is not equal to k dash, sum of the series is 1, and if k is equal to k dash, then we have sigma n equal to 0 to 2 pi I k dash minus k divided by into n divided by n equal to summation n equal to 0 to n minus 1 1. Okay. So, 1 will be summed n times, and therefore, this is equal to n. Okay. So, the when k is not equal to k dash, the value is 0, when k is equal to k dash, the value is n. So, we can combine both the cases. Okay. So, for all k comma k dash varying from 0 up to n minus 1, we can say that sigma n equal to 0 to n minus 1 e to the power 2 pi I k dash minus k divided by n is equal to n times delta k k dash. Okay. Where delta k k dash is a Kronecker delta. Okay. And we know that delta k k dash is equal to 1 when k is not equal to k dash, n is 0 when k equal, sorry, it is 0, it is 0 when k is not equal to k dash, and it is 1 when k equal to k dash. Okay. So, This is how we can find the value of this series. So, we have this n times delta k k dash, where delta k k dash is a Kronecker delta. This orthogonal property. So, now we can see that when k and k dash, okay, uk and uk dash are any two vectors from this set of n vectors, okay, these n vectors are there. So, from this set of n vectors, then their inner product is 0 whenever k is not equal to k dash. This means that these vectors form an orthogonal basis. So, this orthogonal property of the vectors e to the power 2 pi iota k n by n will be used to determine the inverse discrete Fourier transform using the definition of discrete Fourier transform. Let us see how we do this. So, let us derive the formula for the inverse n point DFT. Okay. Suppose u is equal to uk or uj, where j varies from 0 to n minus 1, then uk is the discrete finite discrete transform discrete finite transform of the vectors uj. So, it is given by sigma j equal to 0 to n minus 1 uj e to the power minus 2 pi iota j k by n. We claim that the inverse discrete Fourier transform IDFT is given by uj equal to sigma 1 over n sigma k equal to 0 to n minus 1 uk e to the power 2 pi j k n by n, where j varies from 0 1 2 and so on up to n minus 1. So, let us see how we prove this. So, we have uk is given to us. So, using the definition of DFT, uk sigma k equal to 0 to n minus 1. Okay, sigma k equal to 0 to n minus 1, uk will be equal to sigma k equal to 0 to n minus 1. The value of uk is sigma j equal to 0 to n minus 1, okay, uj e to the power minus 2 pi I j k by n, okay, e to the power minus 2 pi I j k by n, that is uk, okay, sigma k equal to 0 to n minus 1, sigma j equal to 0 to n minus 1, uj e to the power minus 2 pi iota this. Now, this can be written as these are finite sums, we can interchange them. So, we can write as sigma j equal to 0 to n minus 1 uj can be written outside, okay, sigma k equal to 0 to n minus 1, okay, e to the power minus 2 pi I j k by n, okay. Now, let us see, we have to show now okay, let us go to the previous slide. In the previous slide, we have shown that these vectors u e to the power 2 pi I k this e to the power 2 pi I k n by n, okay, satisfy this orthogonal property, that is uk dash, the inner product of uk with uk dash is equal to n delta k k dash. So, here what will happen, here let us see, we will have sigma, okay, we have to multiply uk by 2 pi I j k by n, that we have not done. So, let me write this as we can write like this, sigma k is equal to 0 to n minus 1, okay, uk e to the power 2 pi I j k by n. Okay. So, this is sigma k equal to 0 to n minus 1. I have put the value of uk, this is the value of uk, I have to multiply by e to the power 2 pi I j k, j is already there. So, what I should do, I should take some other index, not j, let me take here m. Let us take here e to the power 2 pi I, because j I am already using here. So, I should not write j here. So, 2 pi I m k by n, let us write this. Okay. So, e to the power 2 pi I m k divided by n. Okay. So, what I do, I consider this right hand side. Okay. I consider sigma k equal to 0 to n minus 1 u k e to the power 2 pi I instead of j I write m. Okay. So, 2 pi I m k by n, then this is equal to sigma k equal to 0 to n minus 1. I put the value of u k from here. Okay. Sigma j equal to 0 to n minus 1 u j e to power minus 2 pi I j k by n, and then multiplied by e to the power 2 pi I m k by n. Now, let us see, I interchange the sums here because sums are finite. So, sigma j equal to 0 to n minus 1 u j I write outside, then sigma k equal to 0 to n minus 1 e to the power minus 2 pi I. So, I remove this here and write this as I combine this and write e to the power 2 pi I m minus j into k by n. So, I write like this. So, I write e to the power 2 pi I m minus j into k by n. Okay. So, we have seen that, let us look at this one. We have seen that sigma n equal to 0 to n minus 1 e to the power 2 pi I n k dash minus k by n, which is the inner product of u k with u k dash. Okay. So, here we can say that we are having the inner product of u m with u j. Okay. So, this is nothing but sigma j equal to 0 to n minus 1 u j inner product of u m with u j. Okay. Okay. So, this we have seen from the orthogonal property. Now, this is sigma j equal to 0 to n minus 1, I write here equal to sigma j equal to 0 to n minus 1 u j, and then delta n times delta m j. Okay. Because inner product of u m with u j is n times delta m j. Okay. So, this is equal to n times sigma j equal to 0 to n minus 1 u j delta m j, and delta m j is the Kronecker delta. So, it will be equal to 1 when m is equal to j, otherwise it is 0. So, when this j will be equal to m, this sum will be equal to u m, okay, otherwise it delta m j will be 0 for every other j which is not equal to m. So, then other terms will be 0. So, this is n times u m. Okay. So, we can see that sigma k equal to 0 to n minus 1 u k e to the power 2 pi I m k by n is equal to n times u m, where m is taking any value from 0, 1, 2 up to n minus 1. Okay. Now, we can replace m by k m by j, okay, and then we have u j from here, u j equal to 1 by n. Okay. This n will go here, sigma k equal to 0 to n minus 1, okay, u k e to the power 2 pi I m I am replacing now with j. So, j k by n. Okay. So, this is how we find the inverse n point discrete Fourier transform. Okay. Now, let us take an example, find n point inverse discrete Fourier transform of this frequency magnitude x k's. Okay, k runs from 0 to n minus 1, x k is given by delta k minus k naught. Delta k minus k naught is equal to 1 when k is equal to k naught, otherwise it is 0, and k naught is any number from the set 0, 1, 2, 3 and so on up to n minus 1. Okay. Now, let us use the n point inverse DFT formula. Okay. So, n point inverse DFT formula gives instead of uj I am writing now xn, okay, because our sequence is xn. For the sequence xn we are using the discrete Fourier transform by xk. So, xn is equal to 1 over n sigma k equal to 0 to n, instead of j we are using n. So, 1 over n sigma k equal to 0 to n minus 1 u k e to the power 2 pi I k n by n. Okay. So, here when you put the value of x k, so xn will be equal to 1 over n sigma k is equal to 0 to n minus 1 delta k minus k naught e to the power 2 pi I k n by n. Okay. Now, by definition of delta, delta k minus k naught is 1 when k is equal to k naught. So, only the term where k becomes equal to k naught, that term will survive, other terms will all vanish. So, this will be 1 by n, and when k is equal to k naught, we have delta k minus k naught equal to 1. So, we get e to the power 2 pi iota k naught into n by n. Okay. So, we get this result. Okay. Now, we had discussed in the first lecture on DFT, how we can calculate DFT of a given sequence by using matrix method. Here also the inverse discrete Fourier transform can be determined by using the matrix equation x equal to dn inverse x. Okay. We had used the matrix equation x equal to dn x there. Okay. Here we have dn inverse given by 1 over n into this matrix. This matrix is n cross n matrix. Okay. So, in the first row we have 1 1 1 each. Let us see how we get this matrix. We have this sequence x n is equal to, let us use this one, x n equal to 1 by n, sigma k equal to 0 to n minus 1. We have this sequence x n equal to sigma 1 by n, sigma k equal to 0 to n minus 1, and x k e to the power 2 pi I k n by n. Okay. E to the power 2 pi I k n by n. Okay. So, you can see here when this is k runs along the rows. Okay. K runs along the row, this is k equal to 0, this is k equal to 1, this k equal to 2, and so on, this k equal to n minus 1. Okay. K equal to n minus 1, and we will be writing it as k n. Okay. So, n runs along the columns, this is n equal to 0, n equal to 1, n equal to 2, and so on, n equal to n minus 1, and we can write it as 1 by n sigma k equal to 0 to n minus 1 x k w n k minus k n. Okay. So, we had, if you recall, in the matrix method for DFT, we had taken w n to be equal to e to the power minus 2 pi I by n. Okay. E to the power minus 2 pi I by n. So, here w n to the power minus k n, w n to the power minus k n will be w n minus k n will be equal to e to the power 2 pi I k n by n. Okay. So, we use same w n here, w n equal to e to the power 2 pi I by n. Okay. So, this is when k equal to 0, n equal to 0, w n to the power 0 will be 1. So, when k equal to 0, w n to the power minus k n, it will be 1. Okay. So, we get this 1 here. Okay. And then when k equal to 1, okay, but n equal to when k is taking any value from 0 to n minus 1, but n is equal to 0, again w n to the power 0 will be equal to 1. So, we get first column also 1. This column will be when k equal to 1, n equal to 1. So, w n to the power minus 1 into 1, that is w n to the power minus 1. Then k equal to 1, n equal to 2. So, w n to the power minus 2, and so on. W n to the power minus n minus 1 when k equal to 1, n equal to n minus 1, and similarly we get the last row. So, 1 by n, this 1 by n comes here. Okay. X k is the column vector. Okay. X naught, x 1, x 2, and so on, x n minus 1, and this matrix w n to the power minus k n, this matrix is here. Okay. So, d n inverse is this, d n inverse will be multiplied by x to get the sequence x. Now, let us discuss the Parseval's theorem, Plancherel theorem and Parseval's theorem. Suppose x k and y k are discrete Fourier transforms of x n by n. Okay. So, x n equal to sigma x k, k is equal to 0 to n minus 1 e to the power 2 pi I k n by n. and by n will be equal to similarly sigma k equal to 0 to n minus 1 by k e to the power 2 pi I k n by n. Okay. So, that those x k y k are discrete Fourier transforms of the sequence x n by n. Then the Planchel theorem states that sigma k equal to 1 to n minus 1 x n by n bar is 1 by n, sigma k equal to 1 to 0 to n minus 1 x k y k bar. Okay. So, x n by n bar, x n you multiply by y n bar. Okay. What we will get? See, x k from the definition of, we are taking the right hand side to prove this equation, to prove this theorem. So, by the definition of discrete Fourier transform, x k is given by sigma n equal to 0 to n minus 1 x n e to the power minus 2 pi iota n k by n, and by k will be given by sigma m equal to 0 to n minus 1 by m e to the power minus 2 pi I iota m k by n. Okay. So, let us take the right hand side of this equation. So, 1 by n sigma k equal to 0 to n minus 1 x k by k bar. Okay, will be 1 by n sigma k equal to 0 to n minus 1, then you put the value of x k, you put the value of by k conjugate. By k conjugate will be conjugate here. Okay, by k conjugate equal to sigma m equal to 0 to n minus 1 by m conjugate e to the power conjugate of this quantity. So, we get 2 pi iota m k by n. Okay. So, this is what we get in this. Okay. Let us now see what happens to this. So, 1 by n sigma k equal to 0 to n minus 1, we can write it as 1 by n sigma k equal to 0 to n minus 1, we put the two sigma together, sigma n equal to 0 to n minus 1, sigma m equal to 0 to n minus 1, then x n by m bar, okay, x n by m bar e to the power 2 pi iota m minus n into k by n. Okay. So, e to the power 2 pi I m minus n into k by n. Okay. Now, so now these are all finite sums. Okay, we can interchange and write 1 over n sigma n equal to 0 to n minus 1, m equal to 0 to n minus 1, the summation over k can be brought inside. So, x n by m bar sigma k equal to 0 to n minus 1 e to the power 2 pi I m minus n k by n. Now, this is again by using orthogonal property, this is nothing but inner product of sequence by m and by n. So, this is equal to n times delta mn. Okay. So, we get 1 over n sigma n equal to 0 to n minus 1, m equal to 0 to n minus 1, x n by m bar and delta mn. Okay. So, delta mn is Kronecker delta, it will be equal to 1 when m is equal to n, otherwise it will be 0. So, all those values of m, okay, which are equal to n, they give the value of delta mn as 1, okay, otherwise it is 0. So, this n will cancel with this n, and x n by n bar delta mn with this double summation will reduce to single sum. Okay. So, n equal to 0 to n minus 1 x n by n bar, okay, when m is equal to n. So, this is how we get the left hand side, okay, this left hand side. So, this proves the Planchel theorem. Let us see how we get the Parseval's theorem from here. So, we go to a particular case here. Let us take the sequences x n and by m to be same, okay, x n equal to y n for all n. So, when x n is equal to y n for n equal to 0, 1, 2, 3 and so on up to n minus 1, then from the Planchel theorem what do we get? Notice x k by k bar will be x k bar now, because by n and x n are sequences are same. So, x n x k bar will be mod of x k square, and here x n bar will be mod of x n square. So, we have this result, sigma n equal to 0 to n minus 1 mod of x n square is equal to sigma k equal to 0 to n minus 1 1 over n times this, okay, is equal to this. Yeah. So, we have sigma n equal to 0 to n minus 1 mod of x n square equal to 1 by n sigma k equal to 0 to n minus 1 mod of x k square. Okay. So, we get this result. So, this is Parseval's theorem. So, if f x n k equal to x k, that means discrete Fourier transform of the sequence x n is equal to x k. Earlier when we started, we had written the notation for the discrete Fourier transform as d of x n k equal to xk we had used earlier, but here in this shifting property d is replaced by f. So, there is just a change of notation, but it is the same thing. So, f of xn k is same as d of xn k, it is equal to xk. So, then this shifting property says that if you multiply xn by e to the power 2 pi I mn by n, then the discrete Fourier transforms shift to the right, okay, it becomes xk minus m, where m is some integer. So, let us use the definition of discrete Fourier transform. We can see that this xk is now given by sigma k equal to 0 to n minus 1 xn e to the power minus 2 pi I kn by n. Now, multiply xn by e to the power 2 pi I mn by n. Okay. So, we will replace here xn by xn e to the power 2 pi I mn by n to get the discrete Fourier transform of this sequence. So, we have sigma k equal to 0 to n minus 1 xn e to the power 2 pi I mn by n into e to power minus 2 pi I kn by n, and this I can write as sigma k equal to 0 to n minus 1 xn e to the power minus 2 pi I k minus mn into n by n. Okay. And by definition of discrete Fourier transform, this is discrete Fourier transform of xn sequence. Okay. So, here this k, now corresponding to this k we have xk here. Okay. So, here this k is replaced by k minus m. Okay. So, we have the discrete Fourier transform xk minus m. Okay. So, when you multiply xn by e to the power 2 pi I mn by n, the discrete Fourier transform shifts to the right, it becomes xk minus m. Okay. Now, another shifting property, suppose dxn k equal to xk, then dxn minus mk, okay, dxn minus mk is equal to xk e to the power minus 2 pi iota km by n. Okay. Let us see how we get this. So, we use this right hand side by definition of the discrete Fourier transform, it is sigma n equal to 0 to n minus 1 xn e to the power minus 2 pi iota kn by n, and we are multiplying it by e to the power minus 2 pi I km by n. So, then the summation is over n here. So, I can bring it inside sigma n equal to 0 to n minus 1 xn e to the power minus 2 pi I k 2 pi minus e to the power minus 2 pi I k, and we get m plus n divided by n. Okay. And so, let us now replace n plus m by j. So, when we write n plus m equal to j, then n earlier was equal to 0. So, now j will be equal to m, and n was equal to capital N minus 1. So, j will be n plus m minus 1. So, n becomes j minus m. So, x j minus m e to the power minus 2 pi I k j by n. Okay. And therefore, this let us replace j by n. So, n equal to m to n plus m minus n, x n minus m e to the power minus 2 pi I k n by n. So, this is nothing but the discrete Fourier transform of the sequence x n minus m. Now, convolution theorem, suppose x equal to x n equal to 0 to n minus 1 is one sequence, by n equal to 0 to n minus 1 is the other sequence of complex numbers, then their convolution is defined as x star by n n. Okay. Sigma m equal to 0 to n minus 1 x m by n minus m modulo n. Okay. This theorem says that the discrete Fourier transform of this convolution of the sequence x n and by n, okay, x and y, this discrete discrete Fourier transform of this convolution of the sequence x and y, okay, which we denote by this notation, is equal to sigma m equal to 0 to n minus 1 x m by n minus m modulo n. Okay. So, which is nothing but when you take the inverse discrete transform, it is x n into y n. X n is the discrete Fourier transform of x, and y n is the discrete Fourier transform of the sequence y. So, discrete Fourier transform of, so we can in other words we can say that discrete Fourier transform of x star by n. Okay. This is equal to x n into by n, that is product of the this DFT of the sequences x n by. Okay. So, discrete Fourier transform of the convolution of the two sequences x n by is equal to product of their discrete transforms. So, this is and I repeat, the convolution of the sequences x n by is defined as sigma m equal to 0 to n minus 1 x m by n minus m, and then modulo n. Modulo m is used so that the values of by n do not go beyond this n minus 1, they remain in between 0 and n minus 1. Okay. Now, let us prove this. So, discrete Fourier transform of, we are going to show that discrete Fourier transform of the convolution of the sequence x n by is equal to product of their discrete transforms. Okay. So, let us take this left hand side. Okay. Left hand side will be equal to sigma n equal to 0 to okay, sigma n equal to 0 to n minus 1, this convolution, okay, we are writing here m equal to 0 to n minus 1 x m by n minus m modulo n, and then multiplying by e to the power minus 2 pi I k n by n. Okay. So, this is simply a discrete Fourier transform of the convolution of x n by, and then what we do, these are finite sums, so we can interchange them. So, sigma m equal to 0 to n minus 1 written outside, and inside we write sigma n equal to 0 to n minus 1 x m by n minus m modulo n e to the power minus 2 pi I k n by n. Okay. Now, then this this x m is independent of n. So, I can write it outside the summation over n, and what we will get then, we will get yeah. So, sigma m equal to 0 to n minus 1 x m, and this sigma m equal to, we have already interchanged. Okay. So, x m will go outside the summation over n minus 1. Now, we have sigma n equal to 0 to m minus 1 by n minus m, okay, modulo n into e to the power minus 2 pi I k n by n. So, this, because of this modulo, this is equal to sigma n equal to m to n plus m minus 1. Okay. Okay, sigma n equal to m to n plus m minus 1 by n minus m, okay, e to the power minus 2 pi I k n by n. Okay, because of this modulo. Okay. So, I can write this, this expression as sigma n equal to m to n plus m minus 1 by n minus m. Now, let me write n minus m equal to j. Okay. So, I will be getting j equal to 0 to n minus 1 by j, and here n will be m plus j. So, e to the power minus 2 pi I m plus j into n divided by n, okay, which we can write in as follows, sigma j equal to 0 to n minus 1 e to the power minus 2 pi iota m n by n. Okay. So, first we write iota j n by n into by j, okay, this by j. This is one thing multiplied by e to the power minus 2 pi iota m n by n. Okay. So, this quantity e to the power minus 2 pi iota m n by n will be multiplied to this x m, which is outside the summation over n. Okay. So, this here, okay, and we will get sigma m equal to 0 to n minus 1 x m e to the power minus 2 pi I m n by n, okay, e to the power minus 2 pi I m n by yeah, you can write k, okay, what we have put here, we have put j, right. So, when we put j here, okay. So, I get here this sum as sigma j equal to 0 to n minus 1 by j e to the power minus 2 pi I k j by n. Where are we getting k j? Okay, this is outside, okay. Inside, okay, we are getting here 2 pi iota k n by n, and what we got, okay. So, I put here, okay, wait, I put here this not n we have put as m plus j, okay. So, this should be k, okay. So, this should be k here, not n. Okay. So, what we have here, actually this is now coming to this is nothing but by k, okay. This is by k, and this quantity, okay, multiplied to x m, sigma m equal to 0 to n minus 1 gives you x k, okay. So, we get this and this, okay. Their product is x k y k. Thus, the convolution of the two sequences is the inverse transform of the product of the individual transforms. So, this is how we prove the convolution theorem. With this, we have finished the discussion on discrete Fourier transforms. Thank you very much for your attention.